How Shopify built the Black Friday Cyber Monday Live Globe 2023. Let's look at this blog post. So every year for Black Friday Cyber Monday, we put together a real-time visualization of purchases made through Shopify powered merchants worldwide. This year we are cooking up something big, and in anticipation we wanted to show you how we built the globe last year. Besides going for better visuals, a big focus was performance. We put together an interactive deep dive on how we build and optimized the 3D visuals using technologies such as 3JS and React 3 Fiber. Before we jump in, here's a globe with simulated data that you can play with. The arcs flying around are the most important component. Each one represents an order of being placed in real time, and they travel from the merchant to the buyer's location. This can be defined as a Bezier curve with 4 control points. Each point is a 3-dimensional vector. P0 located at start position, P1 located 25% of the way between start and end, P2 located 75% of the way between start and end, and P3 located at end position. So here, if you want, you can just play around with these values. So here you can see, I'm not sure if the entire thing is, yeah, so this should be visible now. So if, so if I try to drag it here, you can see arc height can be adjusted by moving control points P1 and P2 away from the surface. To render the arc, we created a mesh that is strip of triangles moving along the curve. This gives us the stability to control thickness and have better flexibility for stylizing it with shaders. You will notice however that as you move the mesh around, it disappears from certain angles. We needed a way to make it always face the viewer. The solution was surprisingly easy. The red lines along the curve represent the tangent at those points. Taking the cross product of the tangent with the direction of the camera gives a new vector. This is used in the vertex shader to offset the position so the mesh always faces the viewer. Now I am not really good at this shader code, but this is shader code. To texture the arcs, the UVs of the mesh are defined with V going from 0 at the start to 1 at the end. So a vertex in the middle of the arc would have V been 0.5. Here it is represented with color equal to uv.y. To animate an arc, the current age of it has to be calculated. This is given by this particular thing. The age is normalized to the range of 0 to 2. Age equal to 0, the arc is starting. Age equal to 1, the arc has reached its destination. Age equal to 2, the entire arc trail animation has fully played out. To achieve the dissolve type effect we wanted, we use the UV and the age of the arc and pass that into a noise function. So again, this is shader code. As new orders comes in, these arc meshes are created and added to the globe. They even have their own start time attribute. As the U time value increases each frame, all arcs animate independently. This was the initial setup we had and was based on code we had been using for many years. There are many implementation of arc rendering floating around the web, and it's very common for each arc to have its own mesh, but it's not very performant. In previous years, we were limited by how many arcs we could draw per frame. Rendering over 1000 arcs at once would bring some mobile devices to a crawl. We finally found our solution: instancing. Optimizing the arc. Instancing is a technique where multiple instances of the same base mesh can be drawn at the same time on the GPU. Each instance can have its own unique properties such as position or rotation, but they all share the same geometry and material data. This results in a single draw call. The shared geometry also means that only the vertices of the base mesh needs to be uploaded to the GPU. Without instancing, each mesh requires a separate draw call, as the CPU must send individual data sets to the GPU for each mesh. This increases memory usage and impacts performance. React 3 Fiber and 3JS supports instancing out of the box. But how can a common piece of geometry be used to represent every shape of arc instance. For this, we landed on an approach to deform the geometry in the vertex shader. Instead of computing the Bezier curve for each mesh on the CPU, it was all done on the GPU. Even though instances share the same geometry data, they can have their own unique attribute. These are known as instanced buffer attribute. For each arc, we need the P0, P1, P2 and P3 control points. There are 3 floats for each of this to represent the x, y and z coordinate. We also need a single point for a float for the start time. The data for each arc is then interleaved into a single large buffer. Inside the vertex shader, we can then use this attributes to recreate the curve. Since each vertex has a UV attribute between 0 and 1 depending on whether it is along the curve, this can be used to calculate its position. As new orders come in, we don't have to upload new geometry anymore. This is our new flow. Loop through data until an arc is found with age greater than 2. This means the arc is finished. Calculate the new control point and start time based on the order's origin and destination. Upload the data to the GPU only for that specific area. With this new method, we are able to render tens of thousands of arcs in a single draw call. Our initial benchmarking found we can render up to a million arcs at once on an M1 laptop. This should give us a good deal of elbow room for years to come. City dots, the glowing dots on the globe represent cities with placed orders in the past 24 hours. We debated whether to use meshes aligned to the surface or to use particles that always face the camera. The difference is subtle, but we can choose instance particles with GL dot points since they lead to a nicer glow on the horizon. See for yourself with the slider below. The left side is surface aligned and the right side are billboard points. Fireworks, we really wanted to find a way to celebrate merchants having their first sale. What better way than to have fireworks go off above their city? Similar to our arcs, we wanted to see if all fireworks could be done in a single draw call. We generate the base mesh using 3JS icosahedron geometry and connect triangle strips from the center to each vertex. To give mesh the look of a firework burst, we gradually lower vertices along each trail to simulate gravity. The UVs on each trail are treated the same way as the arc, with V starting at 0 at the start and going to 1 towards the end. This allows us to easily animate the trails bursting outwards. We also use the noise effect from the arc to simulate the burst dissipating over time. This is combined with a delay factor so that the burst trails have a bit of time before starting to disappear. The whole effect really comes together once bloom is added. This globe was the first where we added post-processing effects, and it added the extra visual we were looking for. While the bursts themselves were really satisfying to look at, they were missing a launch trail coming up from the ground. We didn't want to introduce a second mesh for this, so instead we have a additional long triangle strip that starts at the origin and goes to the center of the burst. We added a geometry attribute called isBurstTrail, which is false for any vertex part of that launch trail and true for the burst trails. This lets us drive the animation for each part. Literally animating T from 0 to 1 felt a bit slow, so we experimented with different easing values. Cubic easing gives it the speed we were looking for. We also added some shader uniforms for launch trail height, burst size and rotation offsets. This lets us group together fireworks in a fun ways. The best part is that this is all still one single draw call. Each separate firework has its own start and time attribute similar to the arc, so that they can animate in and out independently. The end result is endlessly fascinating to watch. Camera animation. One of the most delightful feature of this globe was the way the camera moved. You could search the name of any city, and no matter where the camera was at the moment, it would move along a beautiful path until it framed the city in the horizon. The simplest way to go about this is with spherical interpolation. convert the 3D start position of the camera into spherical coordinate, convert the 3D end position of the camera into spherical coordinates, interpolate between the start and end points over time. The spherical coordinates have radius, phi and theta attributes which relate to zoom, latitude and longitude. In order to make sure the camera looks at the desired city as it moves, the look at function on the camera can be used. Ideally, we want the camera tilted down so that it frames the city with the horizon. Offsetting the phi angle slightly downwards achieves the desired effect. There is a hidden problem here though. If you travel to New York or London, everything works great, but watch what happens when you travel to Sydney. Why does the world flip upside down when we visit Sydney? The look at function uses the up property of the camera to establish which way is up. The up property is a reference direction, not the actual upward direction of the camera. Even when camera rotates, the up property stays at 010 unless we manually change it. When the camera moves to Sydney, the angle between up property and the actual upward direction of the camera becomes greater than 90 degrees. This causes the camera to flip. There is luckily a simple fix for that. We need to set the up property each frame and we can use the phi and theta values to calculate it. With that fix in place, we now have a system that works perfectly for any city on earth. Try traveling to Sydney to see for yourself. Animated pins. This globe's main addition was showing insight about individual cities to promote discovery. Small pins pop out of the globe that you could tap to navigate to that city. To give pins a satisfying entrance animation, we turn to React Spring. Here's a comparison of an early pin animation left with the final one that shows how a bit of easing can go a long way to give a polished feel. Airplanes. Did you notice the tiny airplanes flying around the globe? They are one of the many little surprises to discover. They each follow orbits that pass through two random cities. Here's a quick way to achieve the circular motion. Parent the airplane to an empty object. This will be the pivot point. Offset the airplane by a given amount. Rotate the pivot object each frame. The airplane is now orbiting around the equator. Aligning its orbit to pass through two cities turn out to be simpler than we thought. This method works perfectly fine and is suitable for the small amount of airplanes we have. However, we really wanted to see if we could animate all the airplane in the GPU in single draw call. For this to work, we had to replicate the above in a shader. We started by creating the instance mesh. In this case, we can't use separate pivot objects, but we can achieve the same effect with trigonometry in the shader. The airplane material is a mesh basic material, and we can use the on before compile method to modify its vertex shader. This gives the same effect as the airplane pivoting around the origin. Since each instance has its own transformation matrix, we can set it to a matrix representing the look at rotation from before. The airplanes are now rendered in a single draw call on the GPU. Animating the airplanes is just a matter of updating the current time uniform each frame. While we could have rendered tens of thousands of airplanes without breaking a sweat, we settled on a much more reasonable dozen. The only airplane on the globe that isn't instance is a special Shopify airplane that flies across different cities. For this, we use 6 orbits and interpolate between them. To make it look natural, we make the airplane bank when it transitions from one orbit to the next. It also sways horizontally and vertically by following some sinusoidal waves at the height of BFCM, with thousands of otters flying around the globe every second. Hopping onto Shopify airplane was truly epic. Loopy arcs were the source of lot of jokes such as, "No wonder my order took 6 weeks to ship." Apparently it was doing backflips in the stratosphere. Having an order do a loop in outer space is certainly not the most efficient way of getting it from point A to point B, but they sure add a nice whimsical feel to our globe. In order to have as much control over the animation as possible, we opted not to use Bezier splines. Instead, we wanted to try defining the animation using keyframe and cubic hermite splines. These are common for 3D animation and give an artist more fine-grained control over the look and feel. Let's take a look. Above is a box that slides back and forth along the x-axis. On the right is a hermite curve made up of two separate splines, the left half and the right half. Each spline is defined by a start and end point as well as a slope or tangent for each point. You can think of each point slash slope pair as a keyframe. The x-axis represents time and the y-axis represents the value. This is what the three keyframes above look in a code. So how do we get the values of the curve for an arbitrary time? For example, 3 seconds. Find the keyframe that comes before 3 seconds and the keyframe that comes after. For a hermite curve with only a few keyframes, we can do linear search. For one with many more keyframes, we could do a binary search. There are also more sophisticated techniques that make finding the right keyframe a constant lookup operation, but for our case we can just do a simple linear search. For time equal to 3 seconds, we find keyframe 1 and keyframe 2, interpolate between both keyframes. Note now that we have both keyframes, we can interpolate between them using the following function. In order to animate more than one property, we just need to create a separate curve for each property. In the example below, we move the box in an arc-like motion. The red arc represents the x position of the box while the green one represents its y position. Here are the curves for moving the box in a circle. In order to get our loopy arcs, we had to combine the arc-like motion with circular motion above. The final curves ended up looking like this. Now that we have a beautiful loopy arc, the question becomes, how do we orient our coordinate system above so that arc flies between two cities? Our friend look at comes in handy once again. This time we use the matrix 4 version of look at because it lets us specify the up axis. This allows us to create a rotation matrix that rotates our coordinate system so that the x-axis lines up between both cities and y-axis comes out of the globe at the desired point. If we want to find the position on our animation curve relative to this new coordinate system, we can apply our look at matrix. Now comes the real challenging part. How do we instance this? The first thing to note is that the geometry of the loopy arc is identical to the geometry of regular arcs. The way the triangles are arranged and billboarded and the way the UVs are used to fade out the arcs with noise are all the same. What's different about loopy arcs are the attributes we upload to the GPU. To describe a loopy arc, we need to upload all the keyframes of our animation curve and some additional data to construct a transformation equivalent to the look at matrix. Each frame is 4 floats of data. Once we added up all the floats we needed to pass to the GPU, we were at 94. That's 376 bytes of data per arc, which turns out it's impossible to upload. WebGL displayed this error when we tried. Stride is over the maximum stride allowed by WebGL. The maximum stride allowed by WebGL is 255 bytes. We started to reconsider our option. We thought about storing the data in a texture, which is a technique called vertex texture animation. This would get around the limits but would add some complexity. Luckily, we ended up noticing that lot of the floats we were trying to upload were equal to 0. You can see this yourself in the graphs above. All the flat slopes are equal to 0 and there are a lot of them. Additionally, a lot of the floats that are non-zero are equal to each other or equal but negated. After identifying which of the attributes were unique, we ended up only needing to upload 17 floats per arc. WebGL could handle that without any problem as it was way below the 255 byte limit. The rest of the values were hard coded or computed directly in the shader. With that, we had the beautiful instance loopy arcs. In retrospect, there are definitely simpler ways we could have implemented this. A combination of Bezier curve and circle equation would have been much simpler and more performant. However, we were curious about experimenting with hermite curves to allow for more bespoke animation. We'll explore this more for a future globe material. In the early stage of the project, we experimented with a wide range of styles for the globe. This idea kept coming back of a hand painted aesthetic. We toyed with this effect like toon shading and ink shading, but eventually we find ourselves drawn to a style that mirrored the look of a risograph print. Implementing noise, a key element of risograph print is the noise that you will see all over them. They are covered with little dots of varying sizes. We eventually tried to implement that as a screen space effect using the React post processing library, but it never felt quite right. We needed to add noise to the water, land and atmosphere materials of our globe. The challenge was how to apply noise to the surface of a sphere with no visible seams and without it stretching or getting distorted at the poles. We tried a few different 2D and 3D noise functions like purling noise, simplex noise and Worley noise, also called as Warren noise or cellular noise. It wasn't until we discovered PSRD noise, and in particular the flow noise one can create with PSRD noise, that we felt we had found what we were looking for. PSRD noise is a variant of simplex noise that ties in 2D and 3D and that supports an animation technique called flow noise in 3D. It's fairly new and was published in 2022. 3D PSRD noise can be applied to a sphere without any modification, and it gives noise with no seams, stretching or distortion. The following example walks through how we apply 3D PSRD noise to a sphere. The number in the bottom right corresponds to the explanation below. Start with a standard 3-dot sphere geometry. The color gradient represents the vertex position visualized as colors. Feed the vertex position into the noise function. It returns a value of 0 to 1 for every point on the sphere. Use a time value to animate it. Change the scale by multiplying vertex position by scaling factor. As the scaling factor gets bigger, the noise gets smaller. With 3D noise, there are no seams, stretching or distortion. Add another layer of the PSRD noise function, again using a fractal sum technique. This creates flow noise. Adding 2 layers of the PSRD noise function to make the flow noise more detailed. Scale the noise. 3D PSRD noise is wonderful, but it's not without its downside. It is computationally expensive, especially when calling the PSRD noise function more than once per fragment to create flow noise. Because of that, we switched to using the cheaper 2D PSRD noise function. However, now we had to fix issues with seams, stretching and distortion. Start with an icosphere. Use the UVs of the icosphere as inputs to the 2D PSRD noise function. Notice the seam. Scale the noise. The seam is a little less noticeable, but it's still there. There is a lot of stretching at the equator and distortion at the pole. The stretching and distortion is caused by the default UV mapping of the icosphere. Switch to a custom UV layout consisting of 6 round planes. There is no more stretching or distortion. Seams are still present, but they will go away after the next steps. Create flow noise by calling 2D PSRD noise function one additional time. Add 2 additional PSRD noise calls. Scale the noise. The seam have now disappeared. Below is a comparison of 2D PSRD noise and 3D PSRD noise. While the 3D noise does have some subtle visual improvements, we opted to compromise for the more performant version. Next time you need to use a noise function, give PSRD noise a shot. Material optimization. The standard shader in Three.js is a PBR shader. It's great for realism, but it's also more computationally expensive, especially on mobile devices. To simplify the shader, we use the on before compile method from before to strip down to only the most necessary parts. It was mostly done through trial and error of removing bits that didn't have effect on the appearance. The final shader was around 100 lines versus the thousands in the standard shader, and we switched most to be the vertex based instead of fragment based. Can you tell the difference? The left globe is the PBR one. The stars in the distance ended up using PSRD noise as well, creating a really nice starry sky shader. Only ends up taking a few lines of code. Start with an icosphere with the same UVs as our globe. Use the UVs of the sphere as inputs for the 2D PSRD noise function. The noise is not animated because a time value is not given as an input. Scale and stretch the UVs. Feed the noise to the power function, increasing the exponent filters the noise so that only the brightest parts remain. Multiply the color by an intensity factor to add more bloom. Wrapping up, building the 2023 BFCM globe was a journey in pushing the boundaries of what is possible with instancing and WebGL. We look forward to sharing what we have been cooking up for this year's globe.